So now on to temperature. Temperature is a measure of the amount of kinetic energy particles have. So that's moving energy. The higher the temperature, the faster the particles move. Because if the temperature is increased, particles have more kinetic energy, therefore they're going to move more quickly. Kind of like when you have more energy, if you're active, you want to do something. Particles are the exact same way. So here's our example of our practical setup. The same practical setup as before. This is low temperature. So I'll click play here. The reactant particles are coming in. They're quite slow. They'll collide with the solid reactant, and you're going to get a chemical reaction with a product being produced because there's enough energy in those particles coming in to overcome the activation energy. We can see our volume of gas produced. There's a bit happening. The slope flattens out over time due to the decreasing number of reactants, and looks like that. Now let's go high temperature, indicated by the red, kind of like a field of lava. Now look at these, how quickly these are coming in. So they're going to be more collisions happening more often. Okay, and look at the volume of gas produced, much higher this time, much higher. So this is a big increase in temperature. Now why do you think that might be? So the reasoning behind this is the higher the temperature, the faster the reactant particles move. We talked about that already. Particles moving at a high speed are more likely to collide more often than those moving slowly. Okay? Think about it. If you're in a crowded room and people are running around, they're more likely to bump into each other. Particles are the exact same thing. Thus, as the temperature increases, the speed of the reaction increases because you have more frequent particle collisions. Now surface area. This is the third way to change the rate of reaction. Surface area only affects solid reactants. Reactants that have been broken into smaller pieces or crushed have a greater surface area than large whole solids. It's kind of like being able to spread them out. Okay? Here we've got our solid, it's in one clump. So the reactant particles in solution can only kind of attack the outside here. Whereas if you break it up, I'll go down here, if you break it up into smaller pieces, then the reactant particles in the solution can kind of react with all of this outside surface. And if you add all of this surface area together, it's much greater than one big clump here. Okay? Now the way that we show this in this little demonstration or this little interactive is one flat solid particles for surface area here, and here it's kind of clumped up a little bit, 3 different clumps. Okay? Greater surface area to react. You've only got one line here that the particles can hit, but down here there's lots of different avenues for attack, so that's why these particles are coming in at different angles. Okay, this one's only coming down kind of one side, this one's going in up, down, left, right, everywhere. Okay, so you're going to get the reaction happening more quickly. If you break or crush a solid reactant, it has a higher surface area. More of the surface is exposed at one time. And this allows for liquid or gas reactants to collide with more of the solid surface at one time. This is the same concept behind maybe tablets that dissolve in water and then you can drink it. Okay? It happens more quickly. The more collisions occurring at one time, the faster the reaction is proceeding. The last thing I want to focus on is catalysts, what they are. Catalysts are something that you can add to a reaction that's speeded up, but they're not used, so they're really handy. You can use them again and again and again. The catalyst is always there, okay? Kind of like your stuffed teddy bear or something like that, that you can always kind of rely on. They're there to help the next reaction occur quickly. I don't know why I talk about teddy bears. Anyway, catalysts are used all the time inside the human body. Human body has lots of reactions going on, and there's lots of catalysts that are present in order to speed up those reactions. Catalysts found in living things are called enzymes. So inside your body there's enzymes, okay? Inside your dog and cat there's enzymes going on. If we're talking about an inorganic, so a non-living catalyst, it's just referred to as a catalyst. So this is a bit of a representation, quite simple, of an enzyme. So you've got our enzyme, we've got 2 different shapes here, and they're called active sites. So that's the place where the reaction can happen, okay? So the reactant particles will come in and hang out inside this little shape here, and they'll react, and then they'll be free to leave. The reason why we've got specific shapes here is because enzymes can only catalyze very specific reactions. Okay, if the reactants don't fit the shape, then it's not going to work. If your reactants are, for this representation, a circle, they won't fit in there. Okay, so it won't work. So catalysts are very specific. So here we've got our reactants. They're going to come in here. They're the right ones because they're the right shape. And this reaction involves them kind of joining together. So maybe this is a synthesis reaction. So that's basically it. Okay. Without that enzyme there, that reaction would take a lot longer to happen. Okay. Again, quite a simplistic representation, but this is what we're talking about here. All right. Here's another sample. Enzyme. This time it breaks it apart. So that might be a decomposition reaction that happens. Okay. Same deal. Guys, we've covered the 4 different types or 4 different ways that you can change rate of reaction. We talked about concentration, we talked about temperature, surface area, and catalysts. If you can remember the 4 of those and the way that they work in order to speed up and sometimes slow down, but mostly speed up reactions, then you're doing really well. Thanks for watching, and I'll see you in class.